Good morning, UIKonf. Can you hear me? Nice. So I'm really excited to be here because this is my UIKonf number 4, and it's the first UIKonf that I attend as a speaker. And today it's the biggest UIKonf ever with 450 participants. Yay! But it's not only that. We are from 41 different countries, as I got to know, and this is also the maximum number for all the UIKonfs before. So push for all the countries, yay! So my topic today is really entangled with what I'm working on, and it's called the end-to-end encryption. It seemed to be trending recently, so you can hear it in the news. So one application or another started using it, or other stuff. So I think it's time to explain it. But first about myself. I'm originally from Ukraine, living in Berlin for quite a while, and was doing iOS development for quite a while. It's actually a bit sad to remember this old times. So as we mentioned yesterday by Agis, the privacy is a fundamental human right. But I think different countries and different governments, they understand it differently. All right? So there is recently this topic of trying to forbid the end-to-end encryption or make it crippled. How can this be achieved? So, of course, with any kind of encryption, you can try to forbid mathematics, go back to the Stone Age, forbid the apps from the App Store, block the internet for those apps, or block their endpoints, or backdoor it. Fortunately, it doesn't work. So no one wants to go to the Stone Age. Some countries trying to block the apps in the App Store, but you can switch the App Store, doesn't really matter. Some countries are trying to block the endpoints of the backends of the end-to-end encrypted apps. For example, the Telegram in Russia. I know that my Russian friends or people who are following this topic have a lot of fun with that before, because they always change the backend endpoints to like Google backends, Amazon backends. But the bottom line, I think, is that it's not really working. All right? Because invention is not possible to forbid, or at least the invention of that scale. So the motivation for this talk is because I think it's important for everyone to understand what exactly the end-to-end encryption means, or it's all about, motivate to think about privacy when implementing the apps, and of course, to do more end-to-end encrypted apps the way we did it. At Wire. That's not wired. Not that wire, all right? That wire. So this is the company where I work in, and I'm the part of the iOS awesome team that is based here in Berlin. We are the pioneers of the end-to-end encryption, rolling out our crypto protocol in 2015, and it's available as a wire for workgroups, all right? Worth mentioning, it's open source, so you can grab your copy of Wire source code at GitHub. It's not only that, it's also live, so you can see our pull requests and all of our fancy Swift and Objective-C code in GPL v3. That's kind of sad, right? So how we proceed? First, we define what the end-to-end encryption is. Then we see what is necessary to implement in your iOS app to keep the user privacy in the way of having the end-to-end encryption. And then we'll do a little bit of a sneak peek into the future of the end-to-end encryption as we see it. So what does exactly mean end-to-end encryption? So let's say the sender would like to send a message to the receiver. In our case, it's Foxy sending to Froggy, all right? In the context. The context means people want to read what you're sending, all right? Fairly easy. We have a solution. It's known for a long time. The Diffie-Hellman key exchange allows you generating the public and private key pairs on both ends to establish the secure channel by exchanging the public keys. Then the shared secret is formulated. The shared secret is not known for the attacker, and we're all good. Except when you're not online. So basically, with HTTPS, you know that both endpoints are online to give you to exchange the public keys. When with the messaging, you never know if the receiver of the message was online, is online, or is ever going to come online to give you the public key, right? But there's, of course, a solution to that. It is possible to publish the public key in advance. So when you publish your public key in advance to the backend, then the person who would like to send you a message can fetch this public key and then create the session, the end-to-end encrypted session with you by having this, establishing the shared secret. So it's called the pre-key wire. But another problem is authenticity. What if someone replaces this key on the backend? The service, knowing it or not knowing it, is trying to impersonate one of the users who we would like to talk to, and then create the relay channel, basically the G-man in the middle attack. How we fight this? Well, of course, there is a way, and encryption knows it, the key verification. It is possible to create the key signature and publish another public key. That would be possible then to verify the signature of the key that is published, the public key of the published on the backend. So in HTTPS, we have the authorities, we have these chains of trust where we can have our trusted certificates in a keychain, and we can therefore know the authenticity of the signature. Unfortunately, in the messaging, we have to check the fingerprints, which is basically the hashes of the signatures. Well, you can do a video call to this person to check the signature or meet in person. This is called the fingerprint verification. But the forward secrecy comes. So imagine this malicious agent is recording all your encrypted messages, even though it is not possible to decrypt. At some point, the shared secret could be revealed. And if the shared secret is revealed, it's possible to go back in time and decrypt all your old messages. This sucks. Right? So it is the cryptographers were thinking about it, and of course, it's really easy to roll the key forward. You can hash the key and get the new key. There is no going backwards from the hashing function, of course, so in this way, we're safe. But then comes the backward or future secrecy. So if one message was decrypted, then the malicious agent can continue decrypting your messages going forward, right? If they know how you hash the key or like which salt are you using, which is kind of sucks as well. Oops. So there is a solution to that as well. Whenever you send a message to someone, you're also including your new public key that you generate. And therefore, with this new public key, it's possible to create the new shared secret. And this public key is, of course, signed. Then comes the problem number 5. I mean, it's the last problem, all right? The problem number 5 says, if somebody takes your phone, this phone contains the encrypted messages with their signatures. So therefore, it's possible to figure out who was sending the messages because of the signatures. So the signatures, they have the upside and downside. You can always verify who is sending, and you can always verify who was sending. So in the court, this could be an ultimate proof that you sent this message because it has your signature, and only you possess the private key for this public key. There's also a solution to that. So we can derive the signing MAC key from the shared secret. And if it's done in this way, then both the sender and the receiver can sign the message in the same way. So in this way, it's not possible to say who exactly signed the message, because the receiver, when the app runs, knows who signed the message because it was just coming from the network channel, and only sender and receiver has this key. Right? But if the court seizes the phone and they start digging, not possible to say. In theory, right? Fortunately, the court nowadays accepts the screenshots of messengers, and it doesn't really work. All right. So the thing is, this end-to-end encrypted messengers, as they come to be available nowadays, they were not possible before, in the ways that there were no good protocol to solve all these problems and of the computing power. So before the elliptic crypto, we had to use the prime numbers for asynchronous cryptography, and the CPUs were really slow, especially the mobile ones. And yeah, this protocol is called Proteus that I explained to you. But even the best protocol can protect you from backing up all your conversations to iTunes. So what's the problem here? If we don't even trust our backend to store the messages of users, why should we ever trust the iTunes or the iCloud, of course? So the problem with that is Apple is really trying to back up all your stuff from the apps. And when they do so, it lands on Apple backend unencrypted. And when it's landing on the Apple backend, if you're an activist or you're a person of interest for the government, they could issue a court order to read all your iCloud backups. And here are your messages. So it's actually really easy to protect from that. Yeah, you see the talk is coming to iOS development. So you can really easy to remove something from iTunes backup. Another thing that you have to care about, image metadata. Whenever you take picture, whatever API you're using, you get a JPEG. This JPEG has nothing extra, you think. It has everything. So it has device location, phone model, other metadata. So when you send it through the network, the receiver knows your location. Is it good? All right, so it's really easy to remove it. If you have an image as a data, you can read with the core image, image.io, create the image destination, and erase all the metadata properties from it. CallKit. So in iOS 10, Apple introduced the new fancy calling application integration way called CallKit. So the calling applications could be the first-class citizens on the platform. They could do the calls, they could interrupt users with the calling screen. But unfortunately, there was a crucial bug that all the call history was synchronized across all devices. Again, it goes to Apple backend, so kind of breaks all the encryption for us. Fortunately, they fixed that. They heard us. All right. And of course, if we don't trust our backend, we don't trust iCloud, we don't trust iTunes, should we trust the push notification service? Of course not. So whenever you send a push message, it goes through the Apple backend. It has to go through the Apple backend. And if we put the message that you send plain text in the push notification, this breaks the purpose. So fortunately, there is a way to solve this problem by using the VoIP APNS. So when your app receives this VoIP APNS, let me show it on diagram. So the sender sends the message to the backend. Then backend can send the VoIP APNS. It's empty, so it just has some service fields that we include. And then this VoIP APNS lands on the receiver's device. Then the receiver device had a chance to run in the background. So the intent of this is to establish the VoIP session. Of course, this could be a call initiation message, but as our backend doesn't know the message content, it's really hard to tell. So for any message, it sends the VoIP APNS, then the app starts in the background, and then the app can go to the backend, fetch the encrypted message, decrypt it, and show the local push. Of course, there are problems with this approach. So whenever your app is running in the background and trying to fetch something, it can fail. Whenever your app is trying to basically replace the push functionality in the way, it could fail. But there is a way around it. So this background fetch thingy, it was introduced, I think, in iOS 7, maybe. There is a way to tell that your app requires fetching the content time to time, even in the background. So you can make iOS start your app time to time, and then just go to the backend and check. Maybe there were new messages. Maybe you were offline. Maybe you missed the push. It's really useful. Unfortunately, everybody seemed to love share extensions, and it's a separate process. It requires inter-process, like it doesn't have inter-process communication. It requires the file synchronization. And as I mentioned before, the key rotates. So when we send something, we have to update our key information stored on disk in a synchronous way. Well, this is a whole another topic, so maybe read our Medium post about it. And of course, the big chats. So the Endtoend encrypted apps seem not to support that much of the big chats, and there's a reason. So whenever you send a message in a group chat, it has to be delivered to every endpoint, every receiver. And at Wire, we support multiple devices. So you could have your phone, your Mac, your Android tablet, whatever. And each has its own key information. So whenever we send a message in a group conversation, it has to be multiplied by amount of participants and by amount of participants' devices on average. So if you send in a conversation that has 100 participants, the message of a 1 kilobyte size, which is fairly reasonable, you get to upload 500 kilobytes of data. That's a lot. So what's coming up next? How we want to fight this big size chats problem. How we want to fight this amount of messengers that we have, right? One of the ways is the new protocol called messaging layer security. So where it's coming from? It's the EATF initiative, and it's supported by quite some vendors. I wouldn't read them out as the F word. And yeah, as you see, different companies, they care about the secrecy. Like, even in the big company, you can have a department that cares about the privacy of users and the one that doesn't. So the work is ongoing, but the Facebook guys, with the Stanford, they figured out the way to build the evolving key in the group chats in the secure and safe way, so you can have up to 1,000 participants. Yeah, and it's pretty awesome. You can read up about it on the CATF website. Yeah, time for screenshots. That's basically it. I hope you enjoyed it. And there would be a question session, I think.
Thank you, Mike. All right. We have the first question, I guess, directly. Anastasia?
I hope it's not a trick question, because...
Yep. Awesome.
Thank you. I'll ask 3 questions, like, peer-to-peer. My question is super simple. How often do you rotate key? Do you rotate it with each new message?
Yeah, so the key rotated with each new message until you receive another message from the other side. When you receive another message from another side, you have a new public key that you can use to create the new shared secret using Diffie-Hellman session initialization. So basically, there's also a little bit of problems around it, because the messages could arrive in the wrong order, right? So we have to keep several keys, roughly 20, 30 keys, before we drop them, because it could be that some message was not delivered and we actually have to decrypt it. But what's good with the hashing, if we receive the messages from far future that just has the hashed key, then, hash we can advance in the future up to 1,000 hashes. It doesn't cost us anything.
Hey. First one, the green one.
It's on?
Yeah.
Yeah, OK, good. You explained that you didn't want to store messages on Apple servers. That's why you sent only this VoIP push and then fetch the message via background fetch. I was wondering why you don't encrypt the message in the push and then decrypt it with the notification extension on the device.
So the thing is, the size of the encrypted payload could be quite big. Then it wouldn't fit in the push. And then we anyway have to fetch it from the backend. So we decided not to build like a solution that has a fork in the middle, just build a solution that has one way of working. And also, the problem is if you missed a lot of pushes and then you receive the push, you anyway has to fetch all the messages from the backend in order to decrypt them properly. Hope it answered the question.
Red microphone?
Yeah, I was wondering, one of the things you talk about end-to-end encryption, but what about all the metadata? Who's sending to who, when, from where, and so on? That's just as sensitive, and the server gets all that.
Of course, the server gets all that, but the thing is you can register with a 15-minute email, first of all, on Wire, and you don't have to include your phone number or share your address book. And the second thing is there is no good or there's always a balance between the user experience and the encryption, right? There is a way to build the ultimate encrypted app that nobody would use, right? Like Wire. No, Wire is actually used. So there is a way to build this kind of system where you would have like a mesh network, and you would relay messages all the time, like in Tor network, and we're actually thinking about it, but the problem is it would be really slow, like with all the images and stuff, and maybe eventually we'd come to this. Right now, this is not the ultimate truth, but the thing is, if you just have your account in a way that it doesn't reveal who you are, then it's not a big deal, I think.
All right. Green microphone.
Hi, great talk. I also have a question regarding the VoIP push. Like, have you experienced any issues regarding Apple refusing your app if you use it for anything but VoIP?
Yeah, so the thing is, we have a plausible explanation for that, right? As I mentioned, we don't really know what is inside the encrypted payload, because, I mean, if we would label the messages with more and more metadata, then it would defeat the purpose of end-to-end encryption. So we don't know if the message is the call initiation or the message is just a regular text message.
But you have actual VoIP in your app, right?
Yeah, of course. We have a calling and video calling, so
Okay.
plausible deniability.
Red microphone.
Does all of these companies implementing this MLS thing imply that I'll be able to send a message from the wire client on my phone and somebody else will be able to see it on an app from another participant or not?
So this is not set in stone yet, but the thing, like on the protocol level, there would be a compatibility because of the new standard. But again, this is a bit of a sneak peek. This is, there's like this XKCD for everything. So XKCD for new standard is also there. If you had like 15 competing standards, 16.1 is the way to go. But this one is especially good because it has a support for bigger chats. So most likely the companies would start using it.
Red microphone again.
The question has less to do with the talk itself, but rather with Wire. How was Wire affected by GDPR? I'm actually confused about, because it seems to have affected basically every European company. How was Wire affected by that?
So just a disclaimer, I'm not working on this GDPR, so the person who works on the GDPR changes are actually here in the venue, I think. I wouldn't bother. But I think we have like a special department that takes care of it, and they're built like, the most prominent thing is, of course, the newsletters, right? Because you have to take now the consent for sending newsletters, and to do so, you send a newsletter, and while it's still possible to do. All right? But otherwise, we had like, before, I think we were on a good pace because we were thinking already about all these topics while we implemented the application, and therefore, we don't have to do that much of changes in the application. We just, I think in the application we'll have some overtake controllers that would ask, okay, if you want to still receive the email notifications and this kind of things, or like retention of the user data questions, but that's mostly it, I think.
Okay. Thank you very much, Mike.
Thank you.